Hello everyone, welcome back. In this video, we'll be taking a look at infinite limits of sequences. So this is the last video we're going to do about sequences. So let's look at infinite limits first. So limits at positive infinity, right? So that means an tends to positive infinity. So the definition for this is that for all m, remember that we had epsilon before, but here we have m. So whenever we're dealing with infinity, so epsilon means really small. We only use epsilon. Epsilon is error. It's the really small. It's 0.000 something. So we use epsilon whenever we're dealing with limits at whenever we're dealing with finite limits, but we use m when we're dealing with infinite limits. So for all m greater than 0, there exists an n such that for all n greater than n, an is greater than m. So let's take a look at this graphically, because that'll make all of this easier. So if you have so what this is saying is, if you have a sequence like this which is tending towards infinity, no matter what m you find, because it says for all m greater than 0, for all m greater than 0, so this is a m, and then we can say this is a n, capital N. For no matter what m we find, for all m greater than 0, there exists one single n such that after which all sequence terms which are greater than this capital N are all greater than m. So if you find a larger m, surely we'll find some n which is larger, after which all sequence terms are greater than m, and that's how we show that the sequence is tending towards a positive infinity. And for negative infinity, that means the sequence is going to negative infinity, it tends to negative infinity. It's pretty much the same picture. So if we have this sequence, no matter what m we find, we can always find an n such that all sequence terms are less than m, for all an is less than m. So that's what basically, it's a pretty simple definition after you guys have seen the finite case. So let's take one look at a simple example. So we're told to prove that the limit of an is infinity. We have to prove that limit of an, which is equal to n square, is infinity. So as always, we'll work with the definition. So let's do the template part of the proof. For all m greater than 0, we're looking for this single n such that for all sequence terms, for all n greater than this n, capital N, an, which is n square, is greater than m. So let's do our scratch work first. Let's do that in a different color. Scratch. So we need to show n square is greater than m. As always, we'll try and make n the subject. We get n is greater than m. So we're going to say choose n equals to root of m. Let's see if that works. Choose n. Remember, we're finding this one n, there exists an n. So whenever it says there exists, we are able to choose it. But when it says for all, we can't choose it because it should work for all values of m. So this n depends on m. So choose, and since n is greater than n is greater, which is equal to root m, n is greater than root m, and n square is greater than m, and which is what we needed to show. We needed to show an is greater than m as it heads to positive infinity, and we're done with the proof. So hope you guys have enjoyed this video. See you next time.